Hello everyone, welcome to the video on Wein bridge oscillator. So this is the basic circuit of Wein bridge oscillator. Yes, this consists of two parts. One part is the bridge part. This is the Wein bridge part. This bridge here is a feedback network. Okay, and it consists of an amplifier, which is a CE two-stage amplifier or a non-inverting amplifier. Okay, means as this is two-stage CE amplifier, you know, one CE will produce 180 degrees, another CE produce another 180, so totally the angle becomes 360 degree, or you can take it as 0 degree. Or you can take a non-inverting op-amp. Non-inverting amplifier means the output is not having any phase shift. So, totally this amplifier stage will give only 0 degree. So, according to the Barkhasan criteria, yes, the loop gain means angle A beta must be 0. So, as this amplifier is producing 0 degree phase, this feedback network has to produce only 0 degree. Means it should not produce any phase. So now, if you see the Wein bridge part consists of 4 arms. That is the reason it is called bridge. Yes, we know the bridge balancing condition. What is the bridge balancing condition? The product of opposite arms impedances. Means here, if you see the 4 arms, in 2 arms the resistors R3 and R4 are present. In one arm there is a series combination of R1 and C1. And in other arm there is a combination of R2 and C2 in parallel. Okay. So now what is the bridge balancing condition? See here, R3 into Z2. What is Z2? The parallel combination of R2 into C2 is equal to R4 into Z1. Okay, what is Z1? Series combination of R1 and C1. So that is the bridge balancing condition. Whenever the bridge is balanced, what happens? When the bridge is balanced, it won't produce any phase. These capacitors won't produce any phase. Suppose if one capacitor produce one phase, another capacitor will compensate that phase. Totally, yes, it works like a 0 degree phase shift network. That is the reason of using R3 and 4 and overall the Wein bridge concept. Okay, because we must have 0 degree from feedback network. Now I'll show the transistorized Wein bridge oscillator. So this is the transistorized Wein bridge oscillator. Yes, it consists of, say, this two-stage CE amplifier. This is stage 1 and this is stage 2. So what happens to the output? Output is having 0 degree phase. Okay, then this is the feedback network. Yes, from the output, yes, the input is given like this. For the feedback network, the input is given. This is the forward path and this is the backward path. Yes, this is the feedback network. And from the feedback network, the connection is to the input of the two-stage amplifier. Okay. Yes, we know the output of the amplifier must be connected to the input of the feedback network, and the output of the feedback network must be connected to the input of the amplifier network. Okay. So now this total acting as feedback network, and the feedback output is across R2 and C2 because we connected this combination to the input of the amplifier. See the resistors R3 and R4 here. See here. Okay. So this R3 and R4, R1 C1, R2 C2 totally acts as Wein bridge. Derive the frequency of oscillations of Wein bridge oscillator. Frequency of oscillations is decided by the feedback network. Okay. Yes, now coming to the feedback network part, these R3 and R4 are used to make the bridge balanced. Okay. Actually, the feedback part is this combination. Okay. If you see the circuit, output is connected between this point and this, as this is ground, this point. Okay. So see here, this is the output. This hole is the output. Yes, between these 2 points, you have R1 C1 series combination and R2 C2 parallel combination. Okay. And another part, the feedback network output is across R2C2 combination, say this, and that output is given to the non-inverting input of the amplifier. Okay. Yes, see here. Yes, here it is the output of feedback network represented by Vf, and the output of the amplifier network is represented by V0. The output of the amplifier is connected as input to the feedback network, hence V0 is also called input for feedback network. Understood? Now, how about to start the derivation? Say this, take the series combination R1C1 as the impedance Z1 and this parallel combination impedance as Z2. So, what is Z1? R1 plus 1 by j omega C1. So, that is equal to, yes, just take LCM 1 plus j omega R1 C1 by j omega C1. Okay. Then, what is Z2? Parallel combination of R2 and C2. Yes, R2 in parallel with 1 by j omega C2. Then, it gives R2 by 1 plus j omega R2 C2 by taking the parallel combination. Yes, now replace the j omega of these two with S. Then Z1 becomes 1 plus S R1 C1 by S C1. Z2 becomes R2 by 1 plus S R2 C2. Okay. Yes, then assume a current. Yes, this total current in this circuit as I. So current is flowing like this from this to this. Totally the current is I. So if you assume the current I, yes, this part also, this total part, totally. Yes, if you assume the current I, what is Vf? Vf is nothing but I into Z2. So what is the feedback factor beta? Beta is, we know, output of feedback network by input of feedback network. What is the output of feedback network? Yes, Vf. What is the input of feedback network? V0. Okay, so if you solve this, yes, see, Vf is, yes, IZ2. Yes, what is I here? Suppose if you see the circuit, what is I? It is the current flowing through these two impedances. Okay, so totally you can write I as the total voltage. What is the total input voltage for this circuit? V0. And what is the total impedance? Z1 plus Z2. Okay, so you can write I as V0 by Z1 plus Z2 into Z2. So now what is the feedback factor? Feedback factor beta is equal to Vf by V0. So simply, yes, you'll get Z2 by Z1 plus Z2. Okay. Now substitute actual values of Z1 and Z2. What is Z1? That is 1 plus S R1 C1 by S C1. What is Z2? R2 by 1 plus S R2 C2. Yes, just I substituted here. After that, I simplified the beta expression like this. Yes, finally I got the beta as this. Now in this expression, replace S with j omega, S square with minus omega square, because S square means j square omega square. J square is minus 1. So S square is minus omega square. So substitute these two. Then I'll get beta like this. Okay. Actually, after this you can do the rationalization to get the frequency of oscillations. Instead of rationalization, I am going in a simpler way. As your numerator is having j omega, simply you divide the numerator and denominator with j omega. Otherwise, instead of doing here, you can do here only. Here, divide the numerator and denominator with s. Yes, here divide the numerator and denominator with j omega. So the numerator becomes R2C1. The denominator first term is 1 by j omega. It is j omega by j omega is 1. So it is R1 C1 plus R2 C2 plus R2 C1. Yes. Now if you divide it with the j omega, yes, omega gets cancelled. You will get minus omega by g into R1 R2 C1 C2. This 1 by j omega, j by j again. So j by j means here 2 j's, j square minus 1. So it is minus j by omega. And if you see here, is as the denominator is having j, we must move it to the numerator. So multiply it with the j and divide it with the j. So the denominator consists of j square again. J square is minus 1. So it becomes plus j omega of R1 R2 C1 C2. Fine. So now, yes, you just take j terms common. Okay, we got like this. If you take j terms common, you'll get like this. total phase shift from the beta network. What is the beta network here? It is the Wein bridge. Back network will give 0 degrees phase only when its imaginary part is 0. Okay. So to have 0 phase shift from feedback network, imaginary part must be 0. Whose imaginary part? It is the beta's imaginary part. What is the beta's imaginary part? See here, omega of R1, R2, C1, C2 minus 1 by omega. Okay. So here, omega of R1, R2, C1, C2 minus 1 by omega is 0. So if you simplify it, I'll get omega as 1 by root R1, R2, C1, C2. Okay, so totally you'll get F is equal to 1 by 2 pi root R1, R2, C1, C2, which is nothing but the frequency of oscillations. If R1 and R2 is equal to R, C1 and C2 is equal to C, means R1 and R2 are same, C1 and C2 are same, then the frequency of oscillations is 1 by 2 pi root RC. Okay, so now if you evaluate the beta expression, what is the beta expression? So this is the beta expression. If you evaluate this beta at this frequency, we got this frequency by making this imaginary part is equal to 0. So totally this part is 0. Okay, if you make this part 0, what is the remaining? It is simply R2C1 by R1C1 plus R2C2 plus R2C1. Okay, then if R1 and R2, C1 and C2 are same, then you'll get beta as RC by 3RC, which is nothing but 1 by 3, which is a very important factor in the case of Wein bridge oscillator. Yes, you must maintain beta of 1 by 3, then only you'll get oscillations. Okay, now after finding beta, what do you have to find? You have to find the amplifier gain A. Yes, now another point, the beta of plus value indicates the feedback network is giving 0 degree phase. Now, yes, we know for oscillations, to get oscillations, mod A beta must be greater than or equal to 1. Greater than 1 concept increases the amplitude of oscillations from a small value, and equal to 1 means you'll get sustained oscillations. First, the loop gain will start from greater than 1, then only the amplitude will increase. After reaching some particular point, some particular required value, circuit adjusts itself to the loop gain of 1, then you'll get sustained oscillations. Okay, so hence mod A beta must be greater than or equal to 1 for oscillations. Now if you substitute 1 by 3 here, you'll get mod A must be greater than or equal to 3. Okay, so this is another important factor in Wein bridge oscillator. Okay, so totally we derived 3 formulas. Yes, the frequency of oscillations, beta value and the gain value. Okay, so this completes the Wein bridge oscillator part. Okay, note down the derivation and practice it. Okay, thank you very much.